Hello, welcome to engineering physics course. Today I am discussing about the quantum mechanics, and first of all I would like to discuss about the origin of quantum mechanics. And for this topic I'll discuss first of all one phenomena which is known as the blackbody radiation. And why this is so important? Because the established Newtonian mechanics or classical mechanics cannot explain this phenomenon. Okay, and it forces us to think about the new theory, or we can say it is the one of the causes for the birth of quantum mechanics. So let's try to understand what do you mean by the black body. So if we want to know what is the black body, it is such an object which can absorb each and every type of radiation which is falling on it. And in other way we can say, when this object is heated up through some external energy, it can emit all possible radiation. So we know that electromagnetic radiation, it consists from the radio wave to gamma rays. Okay, and in between this radio and gamma waves there is a very narrow region which is known as the visible range, right? So that much electromagnetic radiation we can sense by our eyes, right? So this visible range, you all know that its frequency ranges from near about 4.3 to 7.5 into 10 to the power 14 hertz. This is the visible range, right? You all know about these things. So what happened about the black body? So when this body is heated at certain temperature, let's say T, it emits all possible wavelengths. That means it emits from the radio wave to gamma waves, or if there exist any other waves, it also emits that waves, or it can absorb all the waves which is falling on it. So this is the black body. So why it is so important? And for that, if we just explain the black body radiation spectrum, then we can understand that one. Okay, so let's try to understand the black body spectrum, and for that I am taking two axes. So along this axis, let's say this is the frequency, it represents the frequency, and this axis represent the energy density. So right now I am going to do one thought experiment, that let's say there is an black body, okay, and it is heated at certain temperature. Let's say it is at T1. So from the property of the black body, it could emit all possible wavelengths of different colors. Some of them are visible and most of them are non-visible. So for example, let's say it emits the green, blue, red, every light, infrared, ultraviolet, etc. So from its spectrum we can say it emits a spontaneous waves, or there is a spontaneous radiation. That means in terms of frequency we can say it emits all possible radiation from frequency 0 to infinity. So theoretically we can say that one, that it can radiate all possible waves with all possible frequency ranges. and right now it is at T1 temperature, and if we observe its curve, we will find that it is like that one. So if we point out these frequencies, that it is from start at the 0, and this is 1, 2, 3, 4, 5, 6, and all of these frequencies are multiplied with the order of 10 to the power 14. Okay, so that means this is 1 into 10 to the power 14, 2 into 10 to the power 14, 3 into 10 to the power 14, 4 into 10 to the power 14, and so on. So we will get this type of curve. So now let's try to analyze this curve carefully. What we will observe, that if we consider this frequency, that is 1 into 10 to the power 14 Hertz, this energy density axis will get the corresponding energy density for that frequency is that much. For easy to understand, we can think this energy density in terms of intensity. Okay, we can say this is intensity. So the radiation with frequency 1 into 10 to the power 14 Hertz, this is the intensity of that radiation. And we can observe carefully that if we move to higher frequencies, let's say we are right now in the 2 into 10 to the power 14 Hertz, the energy density, or we can say that the density intensity of this radiation is quite higher. That means this light is little bit intense than that of the previous one. Okay, similarly, if we reach to the 3 into 10 to the power 14, this wave, we find that the frequency, the intensity is higher than the previous one, and it is going on in this way. But it is not the continuous event. When we reach certain frequency, or in another way we can say that we will get such an wave. For example, let's say this is it represented by this red wave. We find some color which is much more intense than that all the other frequencies. So we get some peak value here, and this peak value represent that the wave corresponding to this frequency, let's say the 4 into 10 to the power 14 Hertz, although it is in the infrared region. So this wave lead the spectrum, right? But again, if we move for higher frequencies, or we will search for the higher frequencies about their intensity, we will find that the intensity is continuously decreasing, or in energy density term we will find that the energy density is decreasing. So what we will get, try to understand in one words, we can say that in this blackbody radiation spectra, if it is frequency nu, and if it is energy density, let's say it is u nu, we will find such a wave whose intensity is maximum, and this is the color of this black body. Okay, similarly, if we increase the temperature of this black body to, let's say, T2 Kelvin, and here T2 is greater than T1 Kelvin, we will get the same curve like this one. That means for up to certain frequency, the intensity is so low that we can't detect that intensity, or in other words we can say we can detect that intensities, but these are not so prominent. But the whole curve is represented by one critical frequency. We will try to understand this one elaborately later on. But here one thing we should observe, or we can observe here, that this spectrum is for T1 Kelvin and this spectrum is for T2 Kelvin. Here we can observe that when we increase the temperature of the black body, the leading wave, the frequency of the leading wave increases. That means when it was in the T1 Kelvin temperature, the frequency is quite lower compared to the curve for the T2 Kelvin. So let's try to understand this one with some visual phenomenon. Okay, let's think, just erase it one. Okay, so for example, let's say it is at some temperature T1, this black body is at some temperature in T1, and from the properties of the black body, as we know that it emits all the radiation, but the leading radiation corresponding to the frequency of the red light, let's say this one, so it appears to us, it glows like a red ball. So if we plot this one here, this is the frequency and this is the energy density, or we can say this is the intensity. So we will find that this curve represent the peak point at the frequency of greater than 4, or let's say it is 4.3 into 10 to the power 14 Hertz. So this frequency, at that frequency, the energy density or the intensity is maximum. So we will see this black body is right now appears as a red ball. Okay, for lower frequencies corresponding to this 4.3 into the 14 Hertz, and the higher frequencies are not so visible compared to this frequency. Similarly, when we just heated up this black body, so initially it was the red at T1 temperature, T1 Kelvin. It means the leading wavelength is the red one. There are also other frequencies, but these are not so prominent compared to the red one. Right now it is heated to T2 Kelvin, and for that we think that this red body becomes yellow. What it means? It means that right now it is emitting yellow light with maximum energy density. So although I am writing in the green format, but it is yellow light, so it appears like a yellow ball. So what happens if we draw together these two curves? We'll find that if it is the frequency nu and if it is the energy density, or simply you can think it is the intensity, so you will get that for the first case this is like that one, or we'll find this is with high intensity and the corresponding frequency is 4.3 Hertz, which is related to the red light, and when it is heated we get another curve, and the corresponding frequency for maximum intensity is near about 5 into 10 to the power 14 Hertz. Okay, so this is the black body radiation spectrum, where we have taken that there is a continuous spectrum, that is a continuous energy radiation from the black body. And with the basis of this continuous emission of the energy, scientists tried to explain this whole curve, but they failed. They cannot explain the whole curve, or their theoretical result cannot fit this curve. And that point, they tried to find out the new theory to explain this black body radiation. So in the later classes, I will discuss about the classical approach to explain this black body radiation curve, and we will reach the Rayleigh-Jeans law. And this Rayleigh-Jeans law is very good for the lower frequencies, but for higher frequencies, that part cannot be explained by this Rayleigh-Jeans law. And this Rayleigh-Jeans law is completely based on the classical theory, that the classical concept of energy, radiation, etc. And later on, Planck rescued us by using the new idea, which is known as the quantum mechanics right now. And from that quantum mechanical concept, we can explain the whole curve. So this black body radiation is not the classical one, it is related to the quantum mechanical domain. So hope you have understood what do you mean by the black body radiation and what is the curve of the black body radiation. So in the next class, I will discuss about the Rayleigh-Jeans law, and this Rayleigh-Jeans law is the classical approach to explain the black body radiation. And I will discuss in details where is the failure of this Rayleigh-Jeans law, and then we will move for the quantum mechanical treatment or Planck's theory for the black body radiation. So thank you very much for your kind attention.